Greetings. I am Dr. G. Suresh, Assistant Professor, PG Department of Computer Applications, St.Joseph College of Arts and Science, Autonomous, Cuddalore. In this presentation, we will discuss about Ii-Dte-Dce interface. One of the Ii-Dte-Dce interface is EIA232. EIA is nothing but Electronic Industries Association Standard 232. The DT is nothing but data terminal equipment and DC is nothing but data circuit terminating equipment. For communication to occur, there are four basic functional units. They are a DT and DC on one end, a DT and DC on one end, and DC and DT on the other end. The DTE generates the data and passes them along with necessary control characters to the DCE. The DCE converts the signals to the format appropriate to the transmission medium and introduces it onto the network link. At the receiving end, the process is reversed. The DCE receives the information and forwards information to the DTE. The data terminal equipment is nothing but any unit that functions either as a source or as a destination for binary digital data. It can be a terminal or microcomputer, printer, fax machine, or any device that generates or consumes digital data. On the other hand, DTEs do not communicate directly with one another but need an intermediary to be able to communicate. The DCE is nothing but data circuit terminating equipment. DC includes any functional unit that transmits or receives data in the form of an analog or digital signal through a network. At the physical layer, a DCE takes the data generated by a DCE, converts them into an appropriate signal, and then introduces the signal onto the telecommunication link. The commonly used DCE is the modem. The Ii-Dte-Dce interface has many standards. It defines a connection between a DTE and DCE. Each standard provides a model for the mechanical, electrical, and functional characteristics of the connection. The organizations involved in Ii-Dte-Dce interface standards are Electronic Industries Association, that is EIA, International Telecommunication Union, Telecommunication Standards Committee, ITU-T. The EIA standards are EIA232, EIA442, EIA449, and so on. The ITU-T standards are V series and X series. In this presentation, we are going to discuss about the EIA232 Ii-Dte-Dce interface. So this is the interface. In this, we are going to define the mechanical, electrical, and functional characteristics of the connection between the DTE and DCE. First, EIA232 interface. One important interface standard developed by EIA is the EIA232, which defines the electrical, mechanical, and functional characteristics of the interface between a DTE and DCE. Mechanical specification. First, we will discuss about the mechanical specification. The mechanical specification of the EIA standard defines the interface as a 25-wire cable with a male and a female DB 25-pin connector attached to the either end. This is the example of a EIA232 interface. The length of the cable may not exceed 15 meters. That's about 50 feet. A DB25 connector is a plug with 25 pins or receptacles, each of which is attached to a single wire. This pin is attached to the single wire, each with a specific function. The term male connector refers to a plug with each wire in the cable connected to a pin. The term female connector refers to a receptacle with each wire in the cable connected to a metal tube or sheath. In the DB25 connector, these pins and tubes are arranged in two rows with 13 on the top and 12 on the bottom. 13 pins are arranged on the top and 12 pins are arranged in the bottom. Next, we will discuss the electrical specification of the EIA232. The electrical specification of the standard defines the voltage levels and the type of signal to be transmitted in either direction between the DT and the DCE. Ii-Dte-Dce states that all data must be transmitted as ones and zeros using non-return to zero L encoding, that is N or Z L encoding, with 0 defined as a positive voltage and 1 defined as a negative voltage. The amplitude of the signal must fall between 3 and 15 volts or between -3 and -15 volts to transmit data. This is a simple example which explains the electrical specification of the Ii-Dte-Dce. Plus this is 0 to 15 plus the allowable area for the data to be recognized is +3 to +15. A positive voltage recognizes as a 0 and negative voltage recognizes as a 1. The negative voltage is nothing but any signal that falls between -3 to -15 will be recognized as a negative voltage, and that will be considered as 1, and any voltage which falls between +3 to +15 is a positive voltage, and that will be considered as a 0. So anything which lies between -3 to +3 is undefined area, and that is of no use. This is the electrical specification for the sending data. So here the signal drops down, and even though it drops down, it is in the positive side, so it will be considered as a 0. Next, for control and timing, there are 25 pins. Only 4 pins will be used for data transmission, other pins will be used for the control and timing. Any voltage which falls more than 3 voltage, +3 and above, will be considered as on, and -3 and below will be considered as off. For the control and timing, the signal has only 2 states, one is on and the other one is off. The voltage which has a voltage more than 3, +3 will be considered as on, and less than -3 will be considered as off. Only 4 wires out of the 25 available in an Ii-Dte-Dce interface are used for data functions, and the remaining 21 are reserved for functions like control, timing, grounding, and testing. The function is considered on if it transmits a voltage of at least +3, and off if it transmits a voltage with a value less than 3 volts. The electrical specification of the Ii-Dte-Dce defines that signals other than data must be sent using off less than -3 volts and on greater than +3 volts. This is a typical Ii-Dte-Dce interface. This is DB 25 pin connector. I mentioned already that this particular interface has 25 pins, 13 on top and 12 on the bottom. Each pin is connected to a specific wire. So these are the data pins, to name a few, and pin number 2 is used for transmitting data, and 3 is for receiving data. And this is secondary data transmitted, and this is secondary received data. These are the control pins: request to send, clear to send. Pin number 4 is used to request to send signal and clear to send. And this 6 is DC ready, and 8 is received line signal detector, and 12 secondary received signal line detector, secondary clear to send, and this is DT ready, and 19 secondary request to send, and some pins are reserved for future use. This is timing pins. 15, 17 and 24 are considered as timing pins. Other pins 1 and 7 are considered for shield and ground, and 9, 10, 11 etc. are considered for future use. Now we will discuss about the functional specification of the Ii-Dte-Dce. This diagram explains the synchronous full duplex transmission of the Ii-Dte-Dce interface. There are 5 steps involved in the data communication between the DT and DC interface. The step 1 shows the preparation of the interfaces for transmission. The 2 grounding circuits 1 and 7, namely shield and signal ground, are active between both the sending computer or modem combination and the receiving computer modem combination on both sides. This is left side and this right side. Pin number 1 and 7 will be made ready. The first step is preparing for data transmission. And the second step ensures that all 4 devices are ready for transmission. First, the sending DTE activates pin 20, this pin number 20 activates and sends a DTE ready message to its DCE. DTE sends a ready message to its DCE. The DCE answers by activating pin 6. DTE sends a DTE ready message to the pin and DCE answers by 6. The same thing happens in the receiving end also. Next, step 3 sets up the physical connection between the sending and receiving modems. It is the first step that involves the network. First, the sending DTE activates pin 4 and sends its DCE a request to send message. The DCE transmits a carrier signal to the idle receiving modem through pin 8. When the receiving modem detects the carrier signal, it activates pin 8, the received signal line detector, telling its computer that the transmission is about to begin. After transmitting the carrier signal, the sending DCE activates pin 5, sending its DTE a clear to send. This is a pin number 5. It gives a clear to send message to the DT. The remote computer and modem perform the same step. The same thing is done in the receiving device also. Next, step 4 is a data transfer. The initiating computer transfers the data stream to its modem over circuit 2. The DT sends the data through circuit 2 to the DC, that is modem, accompanied by the timing pulse 24. Pin number 2 and 24 used for data transmission, data in 2 and timing in pin number 24. The modem converts the digital data to an analog signal and sends it out over the network. The responding modem retrieves the signal, converts it back into digital data and passes the data along to its computer via circuit 3, accompanied by the timing pulse in pin number 17. Likewise, the responding modem retrieves the signal, converts it back into the digital data and passes the data along to its computer via circuit 3, accompanied by the timing pulse of circuit 17. Likewise, the responding computer follows the same procedure in sending data to the initializing computer. The next step is the final step, that is clear. Once both sides have completed their transmission, both computers deactivate their request to send circuits. The modem turn off their carrier signals, the received line signal detectors, and there is no longer any signal to detect, and they are clear to send circuits. In this way, the DTE transmission happens. This is a pin connection with and without DTE. The DTE is connected to the DC through pin number 2 and the DC answers through pin 3. When both DTs are directly connected, it cannot be connected and it will reflect the signal. So, we need a DTE-DC interface for communication to occur between the two devices. Thank you.